Okay. So I got this, and I put the data in. Is that what you guys got? Anybody else? So yeah, the closer you were to negative 0.88, hey, congratulations. And then the closer you are to 20.5 just about on the y-intercept. Yay. But we all sort of should have bounced around those values. And of course, I'm willing to put a lot of money on nobody got it exactly right because we did it by hand. Did you get it exactly right? I'm glad I didn't put a money value on it. Let me see this. No. I mean, from what you did here.
No.
Yeah. Right. So they got excited. He's like, money? All right. I'm willing to put exactly 0 cents on that. So how do I get that to show up on my scatter plot? Get the line of best fit. What is the line of best fit? Yeah, so y equals negative 0.88x plus 20.5 roughly. Cool. What's up? Everybody all right? I love it when several of you look like you're about to say something and you don't say anything. Okay. So now where do I go to get that to show up? Y equals. So negative 0.88x. Oh shit, should have taken that out of there. Oh well. Plus 20.5 going. Now if it hit graph right now, it's going to be it's going to suck because I forgot to do. What did I forget to do? Zoom? No. I like it. Kick ass. Okay. Is the correlation strong or weak? Well, what was the R value? Ooh. Negative 0.939. What do you guys think about negative 0.939? Today's an interesting day. Everybody be quiet. What do you guys think about negative 0.939? It's pretty good. It's damn good. Yeah, so it's a strong correlation. Does that have anything to do with the next statement? If you study more, you'll definitely make less mistakes. The strength of the correlation does not have a damn thing. I can never say that from this study. Now, from our experience, how do we feel about that? Yeah, but from this study by itself can't say a damn thing to that. All it shows is if I take a snapshot, the people that studied more got higher grades. I don't know if it was their studying that got their grades higher. The test isn't set up to do anything about that. I'd have to start off with, okay, you guys study 5 hours, and you guys study 0, and you guys study 20, and then I could do like an experiment or like a drug testing where the treatment would be the amount of studying done, right? That's nothing like what we did here. We just took a snapshot. You guys semi with me? Okay, so I can never, this answer would be we can't say yes or no. We can't say, not from what we've done. Oh, I got it. Okay, any questions about that worksheet? I want to show you a couple other things. All right, so watch this. I always forget to do this, and I'm glad I remembered to do this. All right, so do this with me. Clear out those first 2 lists. Do you remember the problem we did earlier with these, right? And what did we get? We got, what was it? 3x minus 13, is that right? That one we did earlier today? No. Yes? Now, here's something you wish you knew back in like 90 or whatever, if you took 90 or 110 or in algebra. If you go in here and you put 2 points in, what would I put into L1 for those 2 points? Give me started. Yeah, 4 and 6. And of course 4 goes with -1, 6 goes with 5. Can anybody tell me, before I do anything, what will R be for this? What does R measure again? There's a few different ways. Why is it going to be 1? Because R measures how far away the points are from a line, and any 2 points define a line. The line is going to go through both of them. No? And I'm going to make the calculator do what we did earlier for this. So let's see what it does. If I go to stat, calc, number 4, 3x minus 13 with an R of 1. Kick ass.
And isn't there an option where you could have it automatically set it, copy the equation into the y editor?
I like it. It's like I planted you. So the next thing I want to show you is, I don't know if you noticed, I said earlier, just to forget about this for a minute, you don't have to do this because we haven't used this. We haven't had to use it yet, have we? No. But if you want to, when you do this kind of linear regression, when you do a correlation problem, you can tell it to store the equation into y1, which is the first y equals. So let's see. This example is kind of dumb because let's do this. Let's do something more interesting. Clear these. All right. I'm going to put 1, 2, 3, 4, 5. And I'm going to put 24 there. Can somebody help me out? Give me an idea of the next few numbers if I want this to be an R close to -1. All right, let me say that again. I want the result of what I put in to come out with an R close to -1, which means as the x's increase, the y should decrease because of the negative slope. And if I want it close to -1, they should kind of go a little bit lockstep, not perfect. So give me a good number for the second row there. Second? 22. So you went down by 2, right? Now let's go down by 3 maybe. And let's go down by 3 again. And then let's go down by 1. That is definitely going to be negative correlation. It's kind of a small sample, so we'll see how close to -1 we end up. It's not perfectly lockstep. You guys semi with what I'm saying? I like to ask a bonus question sort of related to what I just did. Obviously, it's going to be a little bit harder, but now let's see. Let's see if our prediction comes true. If we do this, calc 4. Now let's do this as we do this. I love what I just said. Let's do this while we do this. Right here where it says store, right? So when you get to that part of this, hang out there for a second. I want to tell it to put it into y1. And that is a variable. So if I go to vars, right there, y vars, function, y1. So I want to reiterate what I just said earlier. Did we have to do what I'm doing right now before when we did the problem completely? No. So this is only if you want to. But let's see what this does for me. I love it. Some of you guys are like, guess what? I don't want to. That's beautiful. I don't give a shit. That's fantastic. If you like this and you want to do this, I'll show you what it does for you. Calculate. This all looks the same as always, right? We got pretty damn close to -1. That's pretty good. Go us. But now if you hit y equals, what do you see in there? If you did that with me. You see that equation, right? So it just puts it in there for you. It's really nice if they're, more disgusting A and B. This was actually kind of a nice A and B. Okay, maybe? A little bit? Okay. Now, I also want to point out, go back to where we calculate this stuff. We hit stat, calc. Look right below number 4. What's number 5? Quad. What does that mean? Quadratic regression. Quadratic. Oh, what does that immediately bring up in your head? Quadratic. Formula, right? And that's solved in x squared, ax squared plus bx plus c equation, right? So quadratic is parabolic regression. So if I have data that seems to kind of go down and then come back up, I could do like the U-shaped happiness thing where I'm here, apparently. Remember that? Yeah, happy. Jeff is there. If my data seems to have a low point and then high points on either side, I'm going to do quadratic regression. What's this? Cubic, and that's x cubed. If it has kind of like what one of my colleagues calls it a giraffe graph. And I always joke them because, so here's a giraffe graph, right? And I'm kind of like, all right, Corey, it's Corey. There should be blood coming out. Poor guy, somebody cut his freaking front leg. What kind of math are you teaching, Corey? You got these legless giraffes about to fall over. He loves that shit. So anyway, so cubic is just x cubed, which looks like this. It looks like a parabola that kind of fell out. So that's it. And then quartic, and then you got, anybody know what this is?
Logarithmic.
Trouble? I like it. Natural log. Yeah, so you can have natural logarithm regression with a shape like this. Right? Anyway, none of that do we worry about in stats 1. I just kind of want to point these things out to you because if I plot my data and it doesn't look linear at all, it might have one of these other shapes. Whoa, it's freaking me out. I was like, I thought there's some monster about to come get me. All right. Exponential, all this kind of business. Ooh, look at that. Sin regression. No, something. Regressing to the sin. All right. I haven't looked down this far in a while. Need a manual fit. Holy shit. All right. Okay. So, last thing for today. And then I kind of want to do a little bit of a preview of what we're going to do tomorrow. Are there any leftover questions about what we did today? No? Okay. A little preview of what we're going to do tomorrow. I'm going to let us out early because I got a meeting later anyway. That would be awesome if I can get ready for it. So guys, if you had so this last section that's left, that we kind of skipped for a minute, chapter 11, this is where I can test more claims. Now, just to let you know, the bad news is I am going to give you a new chart. It's sort of like a z-score chart, t-score chart. So one thing I want to talk about real briefly is why would there be another chart? And what was the other piece of that? I can't remember. This is called a chi-square. Greek letter chi. Got nothing to do with Dragon Ball, so don't. So the most fundamental reason, this doesn't talk about why it looks the way it does, but why would I need a new distribution? So one thing this does is it talks about standard deviations the same way we've been talking about means and percentages. So I could have a claim like the mean is greater than 9, right? And then let's say n is 70, therefore I know it's normally distributed, blah, blah, blah. You guys kind of with me? And that's what we were doing in chapter 9. A normal distribution, what tells me if it's going to be skinny or fat? These are almost the same at all. He's just a little bit fatter. Yeah, tell me again. Standard deviation. And means fall in this picture that is sort of governed by what the standard deviation is. So the shape of the picture that I use is governed by the standard deviation. So what if instead I had a claim about a standard deviation? So I take a sample to test out a claim. Let's say I think that the standard deviation is bigger than 15 for a test that I gave. So I take a sample of tests and figure out their standard deviation. I want to compare it to this one. Why can I no longer use this picture? How many standard deviations are involved in this picture? You can do it. how many standard deviations go into making this picture? One. Here, I have a claim about the standard deviation of all samples, and I take one sample. So I need the picture that standard deviations live on. Okay, I'm not even sure if you guys are really with me. So when I talk to individual people, like we did with Florida, and I plot their data points, and then I talk to a sample, I plotted their sample greater than 30, it's going to look normal at the end. They're going to have a standard deviation that tells me how fat their distribution is. Great. But now I'm talking about plotting standard deviations. Why in the world would they have the same shape when this shape is governed by what the standard deviation is? It doesn't make any sense. Okay, maybe. So, what we use instead is this chi-squared distribution. It's not the only use for it. I want you to realize this is actually kind of cool. I know I keep saying the z-score formula is basically the same, but how many different z-score formulas have we had this semester? Several, right? We have the x-bar stuff. We have one with sigma, one with s. We have the p-hat stuff. Are you guys with me? Well, what picture do they all relate to for most of our problems? The normal curve. Several different equations all relate to the same distribution, the same picture. Are you guys semi with me? Okay. This guy, the most fundamental kind of definer of what this guy looks like is that. That is sort of like the chi-square equivalent of the z-score formula. So if I have a sample that I take, and I know the whole distribution, the whole standard deviation for all samples, and of course this is the degrees of freedom, I can calculate a chi-square score. Now what's the picture look like? So if I do this, if I have a population, and I take a bunch of samples, and I calculate their standard deviations, and I plot it, the picture I end up with looks like this. Is that normal? No. What is it? Skewed to the right. I love it. And I affectionately refer to it as the Java distribution. No, yes, maybe? Okay. If you don't know what Java the hell is, I'm not sure how to feel about you. It's not that. I'm sorry. It's got a hard wall here, because can these ever be negative? Shit, no. Even if they weren't squared, could they be negative? No. So it's got this hard wall here. So that kind of sucks. What is a really nice thing about the normal curve? What's right in the middle of it for z-scores? 0. And then it's symmetric. So you got -2 and +2, and they're related to each other. Yay. This guy starts at freaking 0 and then goes. It's not symmetric. It's not even symmetric even if I put 0 in the middle, because what's the freaking middle of this thing? Is skewed. So it's got some issues. It's not quite as nice of a distribution, but too bad for us. It's just what they look like. So this would be a graph of all the sample standard deviations, and then I can see where mine falls if I use this formula. The same way that this could be a distribution of all the means, and then if I do a z-score formula for my mean, I can see where it falls in this. Does it fall in the rejection region, for example, that kind of business. So that's what we've been doing. We have this known distribution that I calculate a value for a given sample, and then I can see where it is in that distribution. So if I'm talking about standard deviations, oh shit, I need a new picture so that when I calculate this is kind of like the z-score. It's related to that kind of idea, because then I can see where it falls in the picture. And then I can do shit with it. Is it evidence for something, or blah, blah, blah. Maybe. Now, if anyone's at all curious about this, there's something that I really love that I learned way after I took stats. I can't believe none of my professors ever said this. But the chi-square distribution, one sample of it, one piece of it, is if I took the normal and I just fold it on itself, which is one reason why we call it chi-square. So it's for a degrees of freedom of 1. If I have a degrees of freedom of 1, the chi-square distribution I get is by folding this normal on itself. It's kind of neat. So you can look that up yourself if you want to. I'm not going to go deeper into that for the general class, but it's really kind of neat. So we are actually not going to do hypothesis testing using this. Are you happy?
Yes.
Okay. So what are we going to do? You shouldn't have said you're happy yet because you don't know what you are going to do. Something work. No, I'm joking. Something not as bad. What we're going to use this for is called, and again, this is not my phrase, it's called a goodness of fit. Take that as you want. So here's the kind of problem we would be able to handle with a chi-square distribution. Chi-square distribution. If I roll a die 120 times, how many ones do I expect to see, for example? So E for expect. How many ones would I expect to see? You can do it. If it's a good die, nobody's messed with it, and I roll it 120 times, how many ones should show up?
Six-sided die?
Six-sided die, good point. Normal die, not a D&D. I'm not talking about, oh, look at your hit points. No. 20, of course, right? Does everybody see that? So if I have a uniform distribution, I just divide the total by how many possibilities there are. And when I roll a die, and I'm like assuming it's a normal die, nothing's happened to it, six-sided die, I expect 120 divided by 6 of each of them. So how many 1s, 2s, 3s? Each of them are going to have, I expect them to show up, get out of there with those. I expect them to show up 20 times. Okay. Now, let me ask you this. I'm going to truncate this a little bit. I could make this into a full-fledged hypothesis test, but I just don't. Because I think at this point, especially at intercession, that part of your brain probably needs a break. But to be honest, there should be a whole hypothesis test, but we just go right to the heart of it. If I did roll a die 120 times and I did not get this, would I be freaked out? No. If I got 19, 21, 22, 18, 17, 23, if I got that kind of thing, is that evidence something is weird with the die? What would be evidence that something is weird with the die? What would have to happen? Yeah, I mean, so if you go to the extreme, if I roll it 120 times and I get 121s, that is somebody's special die to pull out in some kind of game, right? You with me? Oh, wait a second. All right, I'm ready. All right. So that's obviously, but in the middle, so this is what should feel like a hypothesis test. There must be some point beyond which is more than we would expect or more than would be usual, right? You guys semi with me a little bit? A little tiny bit? Not really at all? Sure. So for example, let's see. What if I saw, let's make something that maybe doesn't feel like it's too crazy. What if I saw 30 of these guys? You don't work too hard. All right. 30 of those guys, let's say 18 here. Someone's going to have to help me out. 10, where am I at? 10 up, 8 up. Okay, you can do it, Jeff. Now I'm even. Now I'm 9 down. I'm 2 up. I think this is right. Does it come out okay? Let's see. 30, 40, 50, 60. 100 and I'm close, 119. I think I'm just one off, right? Yeah. So let's add 1 to something. All right. Somebody double check. Does everybody see what I'm trying to do right now? Now these are the numbers I would give you in a problem. These numbers. This, why do you think I put an O there? Because it's what we observed. So E is expected. O is observed. So what do you think the very next logical thing is for me to do, based on what we were saying, would be evidence that something's been happening with this die? What should I look at now? If they're all 20s, why would I just stop there and go, because there's no difference. So the next obvious thing to do, you see, it's been a while. I think it does this. It almost doesn't matter what this is. To be honest, we're going to square it in a minute for the very same reason we squared way back when we did standard deviations. So if I do observed minus expected, what do I get? I get 11, -2, right? And of course, what are all those supposed to add up to be? And they do, thank God. They're going to add up to be 0, right? Let me stop for a second. Does that sound very familiar? This is exactly the problem we ran into when we did standard deviations. Okay. So of course, the next thing we're going to do is square those. So again, we're not getting very far away from the idea. I want to see how different these are. Now this is kind of like my Z star. I'm seeing my sample and I'm seeing how different we got. We still have to, tomorrow we're going to focus on the theoretical side. How do I figure out what to compare it to? What's my rejection region? So here I'm going to get 121, 464, 81, 1, 4. Don't add those up. I don't know why I put the bar there. Let's see if this last step makes sense. If so here's Jeff in grad school. If I dropped $5 on the road, I'm gonna risk my life to go get those $5 because I didn't have much anything. I'm like, that's a whole meal. That's 2 meals if we go to survive Taco Bell. So if I'm Bill Gates and I drop $5 in the middle of the road, I'll probably have somebody go get it for me. Yeah, I pay a limit. But it doesn't mean as much to me, right? So in this case, it's not just the difference, the pure difference, it's the relative difference. Relative to how big the expected numbers are. Is that a big difference? So the last thing we do is we divide this by E. So let's see, that's going to be 6.05, I think. That's going to be 0.2, right? Right? Yeah. And that's going to be, I don't know, 3.2, possibly. And that's going to be 4.05. I could be very wrong, so you might want to double check. And that's 5, and that's 0.2 again. Help me out. Is that right? Okay, thank you. And then if I add those up, now real quick, again, if these were all 20s, what would I get here? If these were all 20s, if I actually saw 20s, of course, what would I get here?
1.
No, come on. If these are all 20s, what's the difference? Zeros, zeros, zeros. So 0 would mean it matched expectation perfectly. So obviously that's not evidence that somebody tampered with a die. Does that mean nobody tampered with a die? Just because we haven't found evidence that you're guilty does not mean that you're innocent, right? So it's not guilty to little die. We're like, I'm one of you. So we're just going to do a larger sample. We're going to have somebody else do it, whatever. Different environment. So if I add these up, what do I get? What do I get? I don't know what I get. 13.7. 18.7? Yes? Is it?
Yes.
Why am I so surprised? That is our chi-square score. It's sort of like figuring out Z star. Now, I think I used to do chi-square star, but that just gets a little bit like, what the shit? Let me say this several times. And here's the first time. Never square root this thing. Chi-square is a complete symbol. It's not something squared. It is its symbol. You can't square root the poor thing. It's a part of what it is. You guys with me? Do not square root it. I like it. So is this 0? No. So watch. Here's what the picture looks like. Well, give me a little license in there. 0 would mean we saw 0 difference. So that would obviously be not enough evidence that somebody tampered with. I could see some difference, but at some point, if I get beyond that, that is going to be evidence that somebody tampered with it. So the last piece of this that we need to do is, how do I find what the dividing line is? It's sort of like looking up the Z for your rejection region. It's exactly the same idea. So let's just say, let's see, for this size of a sample, I'd say it'd probably be like around 8. It's probably like 7.9 or 9.2 or something. So in this case, did we make it far enough away? Yeah, we kicked this thing's ass. So this means nobody did shit to the die, or we can't say that somebody did. So this means that's evidence somebody messed with that die. It's not proof, but it's pretty good evidence. So that would be all you have to say at the end. I'm not going to make you do 1, 2, 3, 4, 5. I'm not going to make you do all the steps. We're going to do the 2 most important steps. How far away is far away enough? And then how far away do we get? So our conclusion here would be, we have found evidence that somebody tampered with this die. Why? Because it's so far away from what I expect. Just make sure everybody's with me. If I do this with a die that has not been tampered with, do you guys understand that that's going to show up in here somewhere normally? Of course it is. It's the same thing we've been talking about the entire semester. If I take a sample of something, it's not going to equal the actual average or the actual whatever. It's going to be variations within that sample. So I would be really freaked out if I did get 0, to be honest. That would be a little bit freaky. I expect some kind of difference. But the point, again, just like with the hypothesis test we've done, is not only does it have to be different, it has to be so freaking different that it's evidence that the whole thing, if you did it forever, it would still come out different. Oh, man. How's that? Is that freaky? So tomorrow, I think I've decided, we're going to start with like a group activity. I'm not going to make it a quiz. I'm going to give you guys a break. Right? That kind of goes over the correlation stuff. So, all right. And then we're going to finish up chapter 11. And then the rest of the time is going to focus on review for the final. Everybody got a practice final, right? I know if you didn't. It should have been in the packet of stuff I gave you. You know if you didn't get one. Otherwise, we are done way early, which is fine with me. I don't know how you guys feel. You feel gypped? I'm sorry. Okay.